I don't know if there's anything you want to add. I'm going to just share the link into the chat box, mate. And
I was going to do just a wee brief presentation, if you fancy, Del.
Go for it.
Just so that people. No, let me just share my screen.
Yep.
Right. Can you see that?
Yep. Oh, aye, this is right. Good, man. Forgot about that.
Well, what I wanted to do was just give a little bit of, knowledge or insight into this whole process of navigation and map projections and how it ties to our reality, right? And it's a very difficult topic, so I'm not sure I can do it justice in a short piece of time, but
yeah.
I'd like to at least try and summarize a few of the main things that I think people need to understand or know about, yeah?
Yeah.
So what I'm showing at the moment is the so-called celestial navigation sphere, right?
Mm-hmm.
And if you see on the screen, you'll see a triangle that starts at the top here on P and X and Z. It's it's got this wee curved base and this triangle here, right?
Yep.
On the light blue. And then you'll see on the little sphere in the middle, right?
Mm-hmm.
You'll see another triangle, which is basically the projection of this big triangle that's on the big celestial sphere down onto what they call the Earth, right? And the supposed ball that we're on, yeah?
Mm-hmm.
And these two things, so the triangle on the celestial sphere is called the celestial triangle, and the one on the ball that we're supposed to be living on is basically called the nautical triangle.
Yep.
And this whole setup is basically all you need to really understand to be able to navigate anywhere in the world, right?
Mm-hmm.
Because if you solve this triangle, the celestial triangle, with the help of almanacs and how should I say, ephemeris, so star catalogs,
yep.
then you can basically say, well, okay, on the ball, I am at position A, for example, right?
Yep.
And basically what you're doing is you're taking sightings of luminaries, of lights in the sky.
Yep.
You're looking up tables that have been tabulated over thousands of years, so that you can basically solve these triangles using spherical geometry.
Yep.
And then once you've done that, then you theoretically know your position, at least on this supposed ball. Yeah.
Yeah.
Now all problems of navigation can basically be solved by these two triangles, the celestial triangle and the so-called nautical triangle. So basically they're similar triangles. Mm-hmm. And remember, we've talked about this before, where they basically say that the center of the sphere, of the celestial sphere, is the same thing as the center of the Earth, right?
Yeah, well, so, it's you that's the center of the sphere.
Aye, that's exactly what I was going to say.
Sorry.
So,
right.
Aye, sorry, not to buy in any time, but what they're showing us here is apparently an Earth inside a celestial sphere of stars, right?
Yeah.
Hopefully, we all know now that this all has something to do with vision, and what's actually being depicted here is more of the visible geometry that we've been talking about. But it's not called that, right?
Yep.
It's called something completely different, right? It's called celestial navigation and that kind of thing. So, I hope people can see the similarities here of what's going on, that this triangle on the celestial sphere is very similar to, my visible perception of objects, right?
Yep.
Any object also takes up a position on the inside of my, concave sphere, which is our visual perception.
Yep.
And basically, it's not the Earth that we're on. This is our eyeball that should really be depicted here, right?
Yep.
As far as the celestial spheres goes. Yeah.
Yep.
So, there's quite a few, how should I say, intricacies and details to this, which I'm definitely going to be doing some presentations on. But, the main thing that I want people to take away is that the solving of this triangle, this nautical triangle, is how people navigate all over the world. And you hear all the time that, it can only be a globe because only on a globe does the navigation work, right? Yep. And that's something I'm going to be putting to bed, in the coming month, right, with a selection of of videos explaining how it is just as possible to be on a flat plane and to have spherical vision, and you will have the mathematics working exactly the same way, Del.
Yep.
So that, you know, all of the mathematics that, you know, they use to try and prove their globe actually just works in our favor too,
yep.
as long as we restate the definitions and the words, right, to conform with visual geometry.
Yep.
Because if we do that, then all the there's nothing wrong with the mathematics. They all work in the favor of the flat Earth too, right?
Yeah.
And, you know, I want to put that to bed, and I want to make sure that academics look into it in more detail.
Yeah.
So, you know, there's another slightly more complicated version of that diagram, and I'm showing it now.
Yeah.
But it's basically the same thing, that this little ball in the middle is supposed to be the Earth, and all these fancy lines around here have to do with the paths of luminaries, or the imaginary lines of the celestial sphere.
Yeah.
And you can see that all these things are just big, great circles, right?
Yep.
Yeah. So any circle around the sphere going through both the poles is basically a great circle. So that the whole of this geometry has everything to do with circles, right?
Yeah.
Whether they're on a sphere or whether you've got a circle on a plane.
Yep. Yep.
Right? And we know that circles on planes can be scaled, you know, and there are coordinate systems that we use for that, called polar coordinates, for example, which will work just as well as spherical coordinates on a ball, with the only exception that instead of calling the polar coordinates by the names that mathematicians call them nowadays, we just change the words to also call it latitude and longitude.
Yep. Yep.
And then all these things still work, right, if you factor in vision. So some simple changes of words and definitions and understanding how the geometry of vision works gives you all the explanations that you need to be able to navigate. Yeah. So that's one thing I really want to push, because I'm fed up hearing that argument.
And
that it only works on a ball.
No, well, it was done before that, before anybody thought it was a ball.
Exactly. And it's more of a lost knowledge, right?
Yeah.
It's more the case that, you know, nowadays, you know, if you look back at, you know, Ptolemy's version of the world where they thought, you know, everything was stationary and the stars were moving around you. That is also the assumption that you make in celestial navigation to this very detail.
Yep.
Right?
If you got that there.
How do you mean?
You know, the thing we were looking at earlier, the descriptor.
The descriptor?
I remember the wee page where it was saying that.
All right. Hold on, let me try and find that. I think it's in this one, is it? Yeah.
Yeah, this was it.
That's the one you mean, was it?
That's the very one.
All right. This is, by the way, a very good wee website for people who want to look into this in more detail. It's called harry144.com. I just chanced upon it. But on that website, the guy's got a kind of whole, you know, information about celestial navigation. Yeah. And a very interesting thing was this whole idea of how, you know, to navigate, you have to go through some certain steps. You have to take a sighting of something, right? In this case, it's a sighting of a lighthouse, but it could just as well also be a light in the sky, right? Yeah. Where you don't know the correct altitude of that light in the sky.
Yeah.
Yeah. But you've maybe got two people who are going to measure the angle to that light in the sky. So there's a guy here, you, and a guy here called me, right? And obviously, if I'm further away from this light, then my angle's going to be smaller, right? And if I'm closer to the light, then my angle's going to be bigger. Which is exactly the way we measure Polaris, for example, right?
Yeah.
There's no difference. But if you're out on water and you have a formless, featureless surface, the way water is, right? It's always level.
Yeah.
Then you have no markings, so you have no way of actually measuring distance properly. So all you can do is take two different sightings from two different places and then compare the measurement that you've made.
Yeah.
So if, for example, this guy measures this to be whatever, 30 degrees in 10 minutes, let's say, and this guy here measures it to be 30 degrees in 20 minutes, then there's actually practically in navigation, what they do is they say, well, okay, the difference of his altitude and to my altitude is, let's say, 10 minutes.
Mm-hmm.
And what you do is you then define 1 nautical mile as that length needed to see a difference in altitude of 1 minute, of 1 arc minute, right? So basically, if we want to know how far apart we are, then we both measure to a light in the sky, right?
Yeah.
Then we know at least who is closer to the light, who is further away, and what the distance is apart from each of us. Yeah.
Yeah, and that's using Euclidean principles right there. So, so now what people have to do is imagine that there's a curve now between these two figures, and the me figure is round the bend. How are they going to find each other?
Yep. How would they ever find each other? Yep. And the distances would be wrong as well, right? Because a curved arc is longer than a straight line, right?
Exactly. And his horizontal line is now not the same as you's horizontal line. It's fucking pointing somewhere else.
Exactly. And what they do for certain much of these things, this is also quite, they have things called site reduction tables for marine navigation and for air navigation. And so this is a military website, the National Geospatial Intelligence Agency. Mm-hmm. People can look it up. There's actually quite a few good books in there as well. I'd recommend the American Practical Navigator for anybody who's serious about learning more. Yeah. Very good book. Yeah. But so they use these, tables, and even the name site reduction tables tells you a lot, right? But yeah, to go back to your point here, if we understand that we have spherical vision, right, or that our visual space is not Cartesian, right, not box shaped, and we understand that we're on flat level water, then all these navigational things work just fine, right?
Yeah.
And when people say to me, "Go on, then prove it," that I don't need to, because it uses the same formulas they're already using. Yep. I can literally just turn around and say, hey, it's the same way you're using them. It's just that I'm interpreting it differently, right? Yep. And people might think that sounds a bit like a cop-up or a cop-out. So I'm going to be doing a couple of mathematical papers on that, Del, just to make it very clear what I mean, right? Excellent. And something that I want academics to get their teeth into. So
excellent.
I think that was the main point we wanted to talk there, I think,
Yeah.
I definitely want to point out that to people, that these definitions of nautical miles has everything to do with seeing, right? Yep. We talked about it the last time too, the number 3438, being the number of nautical miles in the radius of the Earth. So they just make that assumption based on dividing the circle using base 60, yeah? And it would seem to be something that's been known for a long, long time. Celestial navigation is no longer part of any curriculum either, just like the trivium and just like perspective. Yeah. So these things are being, removed from our education, let's say, and being replaced with ever more TV screens and images and movies and bullshit, right? Yeah. And people are losing that knowledge, and people can tell them anything and they'll believe it.
Exactly.
So as far as I'm concerned, it's empowering to regain this knowledge and try and get it out there for other people to understand.
Yeah, totally agree, mate. Totally agree. So people need to be clear. The tangible world is Cartesian planar. That's what we know. That's how we operate. That's how we apply ourselves. The visible world is different. Spherical geometry required for that.
Absolutely, and just one thing while I'm at it here. So there's there's two different coordinate systems. One's called polar coordinates, which people have probably already heard before, right?
Yeah.
Which is basically just like concentric circles, right?
Yeah.
You're at that point, and everything going out away from you is the distance outwards.
Yeah.
And the angle, for whatever angle that you're going in, is just measured the exact same way. So this would be an angle, and this would be the distance outwards. Yeah.
Yeah.
And if you compare that to the spherical version, I'm not drawing a very good sphere here, sorry, but just so that you've got the picture. Then you've got, that's a really bad fucking sphere, Gavin. Hold on, I'll draw it below. It maybe makes it better. So there you've got the sphere. I hope you guys can kind of see that, right?
Yeah.
Then latitude and longitude, yeah, on a sphere, right? If let's say I start at position A on a sphere and I'm going to position B, then I have to basically go out along this way and up this way if I want to measure my latitude and my longitude.
Yeah.
But what I'm really doing is just taking a straight run, right?
Yeah.
Across that. Now, if you look at the polar coordinate version, then that's exactly the same. You know, I can have a latitude and of 2 different points, right? And I also have a straight run. So this triangle here, right? And this triangle here are basically, you know, the same thing, right?
Yep.
Except that I'm defining latitude and longitude on a sphere rather than defining latitude and longitude on a planar surface, right?
Yeah. But even their depictions, they will show you that they're always, the observer's always on a plane.
Yeah, exactly. So, you know, polar coordinates on a flat surface where things are just going away from me and I've got an angle left and right to, you know, Polaris, let's say, is exactly the same as what they're doing on a sphere, right? Yeah. Except that it's a great circle of a sphere they're using and no longer just concentric circles on a plane, right? But to solve the nautical triangle that I talked about earlier, right, you basically still have to go through the same things. You have to take a sighting of something. In our case, we're on flat water, right? We know that, right? And we're taking sightings. And in this one, they're imagining us to be inside another big celestial sphere. And they're just trying, you know, they're playing with map projections and things to make us believe we're on one. But it all works just fine with this polar coordinate version, right? And again, I'm maybe going too far here already because I wanted to keep it short and sweet. But I'm going to be explaining all that pretty soon in videos, right?
Excellent. Look forward
to it. And I thought I'd just play with my new wee toy. I got a wee kind of set up here and a wee app so that I can draw wee pictures and stuff and write wee formulas down and my wee whiteboard and chalk.
That's that, mate.
But anyway.
Aye, well, we'll look forward to that, you know.
Yeah, well, I hope you're going to be part of it so that I can explain it to yourself and you can ask pertinent questions and all that, my man.
Of course, as always, mate, as always.
I need people to bounce it off, so.
Excellent. I look forward to it, mate.